So let's put all those gas laws together with what we also know about the stoichiometry of a balanced chemical reaction. So here's a sample problem that really ties together multiple chapters we've covered this semester. If you ever played with those backyard rockets, they had those small solid engines. Their engines are based on this potassium chlorate. When you heat potassium chlorate, it breaks down and gives you solid potassium chloride, but it also produces oxygen gas, and that acts as the propellant in these backyard rockets. So let's say one of those little solid rockets contains 117 grams of the solid potassium chlorate, and we burn it in that rocket motor. How many liters of oxygen are produced, given that we're at a 1.18 atm pressure and they get quite hot, so we'll say it heats up to approximately 550 degrees Celsius. So how do we put all of this together, the gas laws, the balanced chemical equation, to determine what volume of oxygen was produced in this reaction? So the first step, I need to figure out how many moles of oxygen are going to be produced. That's what we need to determine eventually. Right now, I just know how many grams of potassium chlorate I put in the reaction. So I know I can't go from grams of potassium chlorate to a volume of oxygen, but I can go from grams of potassium chlorate to moles of potassium chlorate. So I have 117 grams of potassium chlorate, and I know, based on looking up the molecular weight of this, based on potassium, chlorine, and 3 oxygens, that to have 1 mole of potassium chlorate, I would need to have 122.55 grams of potassium chlorate. So I have approximately 0.9547 moles of potassium chlorate. Now I can get on the way to finding how much oxygen I have, because I know from the balanced chemical equation, for every 2 moles of potassium chlorate that go in the reaction, 3 moles of oxygen are going to come out. So I took mass of potassium chlorate to find moles of potassium chlorate. Now I can find moles of oxygen, and then when I know moles of oxygen, I can use PV equals nRT to find what the volume of oxygen should have been. So I've got 0.9547 moles of potassium chlorate, and I know for every 2 moles of potassium chlorate that goes into the reaction, I'm going to get 3 moles of oxygen out of the reaction. So when I multiply, the moles of potassium chlorate cancel out, and I'm left with 1.432 moles of oxygen. Now that we have moles of oxygen, we can use PV equals nRT, right, to find out the volume of that oxygen. Now that we determine moles, I can find the volume of oxygen under these conditions. So again, volume is our unknown. So just to make my life a little bit easier, I'm going to rearrange the calculation. I can divide both sides by pressure. Pressure cancels out, and my calculation is going to be volume equals nRT over P. One other step that I had to do that I already did was convert degrees Celsius into Kelvin. Again, Kelvin equals 273 plus degrees Celsius. So 550 plus 273. And my temperature is 873 Kelvin. Now I can plug in to determine the volume of this reaction when I have 1.432 moles of oxygen produced. My universal gas constant, 0.0821 liters atm mole Kelvin, times my temperature, 823 Kelvin, all over my pressure of 1.18 atm. Multiply and divide, I get a volume of approximately 82 liters of oxygen produced. Right, a huge volume of oxygen is produced when I burn that solid rocket. And it's that volume of oxygen that's produced that acts as a propellant, pushing that rocket up in the air. So again, this kind of really brings together all of the calculations we've done this semester, because we have to use mass to find moles. We have to use a balanced chemical equation to relate moles of one component to moles of something else in the reaction. And then once I know the moles of the product, then I can do my last calculation using PV equals nRT to find out what's the volume of that gas produced.